Okay, let's put this at 37. Okay. Hi, welcome to the second uncertainty principle lecture snippet. The last one was really good, so you might want to go back and get that one. So now we're going to go after ways people have tried to get around the uncertainty principle. So it's a parlor game. A lot of smart people, even well back in the very beginning. Well, in the very beginning was understandable because they were just trying to understand the uncertainty principle. And many people are still trying to understand the uncertainty principle, including me. But people have tried to get around it. And one of the most famous people to ever try to get around it is arguably the most famous physicist of all times, Albert Einstein. So he really didn't like it. And he kept coming up with experiments to try to get around it, and we're going to go into some of those today. First of all, where did you luck onto? Who's this guy? My name's Robert Nemiroff. This is Physics X, and we're reviewing the coolest concepts in physics with as little math as possible. We're trying to get right to the basic concepts. So this is a course being taught for credit at Michigan Tech. It's no textbook is required. Many times you'll see Wikipedia links, and if you go to the online site, actually currently through Starship Asterisk, then you can click on the links and just be taken to Wikipedia entries that describe in detail, more detail than I went into on what's going on. Okay, so let's start with Heisenberg's microscope. So Heisenberg considered this when he was formulating his uncertainty principle, which is probably one of the most profound statements in physics. So one way to think of this is you have a microscope and you're going to try to illuminate this particle here. And so the way you're going to do that is you're going to shoot, let's say, long wavelength photons at it. But what happens when you shoot long wavelength photons at it to determine its position is you find that you can't determine its position better than the wavelength of a long wavelength photon. So the own recoil then will give you an uncertainty in the photon, which will give you an uncertainty in the position, and will give you a delta x. And that will also create a delta p because the energy of the photon will have knocked this thing left or right, and will create a uncertainty. Now the uncertainty principle can't be beaten. It isn't necessarily created by an observer effect, but certainly an observer effect can get you down, can create uncertainty in what you're doing. So that's Heisenberg's microscope. It's a fundamental way of thinking about measuring something, and it shows that if you try to do a very simple measurement technique, last time I talked about single slit, if you just try to illuminate an object with a photon, you can't beat the uncertainty principle that way. And in fact, in that case, it almost defines the uncertainty principle. Okay, so Albert Einstein wasn't happy with quantum mechanics in general and the uncertainty principle, and so he would continually, for a while, try to come up with ways of getting around it. So one of his earliest ways was what's sometimes called Einstein's slit. So Einstein figured, okay, I'm going to try to predict, here's a photon going toward a slit in a wall. So here's a slit in a wall. So the uncertainty principle says that you can't predict where this photon's going to hit on the wall. Apparently it's going to hit down here according to this picture. But you can't predict that. Einstein said, wait a minute, maybe you can predict it. You've been considering only the photon. Let's now consider also the wall. Let's say you can measure this wall, where this wall is going to go, up and down. You can measure what it's doing. And so let's say the photon got a kick down to here. So you see the photon goes through, and you see the wall gets a kick in the up direction. So then you can say, wait, I'm going to balance momentum and say, oh, I know where that photon's going to go. So Einstein tried to beat the uncertainty principle by also including the momentum of the wall being measured. And so this is all part of the Einstein-Bohr debates. So they would meet and talk about this sometimes for hours, and sometimes at conferences Einstein and Bohr would show up, and there would be people giving papers, but really the best action was behind the scenes when Einstein would confront Bohr with a way of beating the uncertainty principle. And at first it might look like Einstein was right, and then almost always Bohr was able to show that wasn't the way it seemed. And sure enough, when Bohr looked at this in some detail, he found out that the uncertainty in the momentum of the wall. So you can't measure the momentum of the wall precisely. So if you include the uncertainty in the momentum of the wall and the delta x of where the photon was, then you find out that you cannot beat the uncertainty principle. So even if you were to measure the momentum of the wall as accurately as possible, and given this slit of space delta x here, this width, you don't know where that photon's going to end up on the slit on the image screen any better than the uncertainty principle would tell you. So it was a clever try. It was a very fundamental try, but it didn't work. Einstein was not able to outsmart the uncertainty principle that way. But he didn't give up. Next conference. Okay, so here's the solution. Bohr said no. There will be uncertainty also in the wall's position. When everything is accounted for, the uncertainty principle still holds. So if you click on this, you'll be taken to, if you click here, you'll be taken to, if you're able to, the Wikipedia page on the Einstein-Bohr debates. Okay, Einstein wasn't done. He went back to the drawing board and came up with something that he thought was even more clever. And so the way this one works is that you have this box here, and this box is filled with photons. And these photons have energy, E equals mc squared. This is after that, everyone agreed to that. And they're bouncing around this box. So they give this box effectively a mass. And so here you have a scale that's measuring this mass. Then Einstein said, okay, look, we're going to, this should be a delta. I don't know what happened to delta t there. This should be delta E, delta t greater than h because I'm too lazy to write out 4 pi. So if you now open a slit on this box and you let out a photon, where is that? I think that's here. Here's where the slit opens. And you let out a photon at a very specific time. So this slit is only open for a very small time, delta t. Then he said, once this photon leaves, then you will know what the energy of the photon is, E. You will know when it left. You'll know the energy of the photon to arbitrarily good accuracy, delta E. You'll know when the photon left with arbitrarily good time, delta t. And therefore, you'll know the energy also because this thing will have moved down, the dial will have moved down, the box will weigh less because it's in a gravitational field, gravity's pulling it down. So you'll be able to beat the uncertainty principle. You'll know. And so Bohr was a little bit worried about this for a while, but he was able to, on pretty short order, cleverly reply. And Bohr again said no. When the photon leaves the box does sag, I guess actually it moves up because it has less energy. However, the uncertainty of the clock in the gravitational field includes gravitational slowing because this was after general relativity. And so you don't know exactly where this box is in the gravitational field. And so an uncertainty in the position of the clock leads to uncertainty in the slowing of the clock, which leads to uncertainty in time. So all of this ends up, if you do all the details, the uncertainty principle holds again. So Einstein spent a lot of time trying to beat the uncertainty principle, and he could not. He couldn't predict things that would come out of that box. He couldn't beat the uncertainty principle in predicting energy and time. Which brings us, however, to the other uncertainty principle. Usually there's delta p, delta x, or delta p is actually in the x direction, is greater than h bar over 2 pi, but we'll call it h. So here we have the same kind of principle as delta E, delta T. So let's look at that in some detail. So this is not exactly like the regular uncertainty principle of delta P, delta X. The delta T really refers to the measured lifetime of a given state where energy E is known to accuracy delta E. So a state exists for only a time delta E cannot have an energy better defined than delta E. So there are ways of just looking at your measuring a photon at an exact time that you might appear to be beating the uncertainty principle, but they don't work. In actuality, you have to refer to a state that exists for a time delta t cannot have an energy better defined than delta E. That's what really this uncertainty principle means. And you should also be careful of the other uncertainty principle. So you have to be very careful in defining what it is you don't know and what you can't predict to better in a certain amount. It's commonly said that the uncertainty principle can be violated for short times, delta t. And I think that's a misconception. The energy of a state, the energy state of a particle can remain unknown, but we'll look at this in a lot more detail when we talk about virtual particles, and we will have talks on vertical particles. But essentially, the uncertainty principle can't be beaten, even for very short times. Okay, and with that, I will wrap up a little bit earlier than 15 minutes, and we'll talk about different concepts and misconceptions in physics next time. See you then.